Hello and welcome everyone to another episode of Wissenschaftler's Wohnzimmer, this time sitting room science, since we have another English episode. I'm very happy to welcome you all here to this episode where we will learn about how to measure the sea level in the Arctic Ocean when there is so much sea ice. How do you actually do this? And we will hear all about it from Francesca Doglioni. I missed to ask how to pronounce your last name correctly, but you can clarify this, hopefully. She's working at the Alfred-Wegener Institute, the same as the rest of tonight's moderation crew, and I'm very looking forward to your talk. And so we will introduce ourselves as well. So my name is Francesca Pausch. I'm a PhD student at the Alfred-Wegener Institute. I'm working with phytoplankton, the small microalgae in the Southern Ocean, so on the other side of the globe, but there's also ice, sea ice, most of the time. And I'm curious to learn more from Francesca, so I pass on to Nathan.
Hello everyone, my name is Nathan. I'm also a PhD student at AVI in the climate dynamics section, so I do some climate modeling, some ocean modeling, and so I'm very interested to see what Francesca has to say.
Yeah, good evening, everyone. I'm Rebecca McPherson, and I'm a postdoc at the Alfred-Wegener Institute. And Francesca and I actually work in the same group. So we're both physical oceanographers, which means that we use actually instrumentation. So a little bit the opposite of what Nathan does with models. So we use instruments in the ocean, or in Francesca's case, in the sky, to measure the ocean. And so I in particular look at the melting of the glaciers in Greenland up in the Arctic. And so it's pretty cool to combine all of our knowledge here, so mine in the ocean and Francesca's above, to see what we can actually determine about the ice and its eventual fate, I suppose. And so with that, Francesca, it's up to you.
Thank you all. So my name is Francesca Doglioni. That's actually how one would pronounce it. And let me just share my screen so that I start. Can you see it well? Yeah, perfect. So as Francesca already said, I'm also part of the AVI. I'm doing my PhD at AVI, and in particular, I'm part of the physical oceanography section, as Rebecca was saying, which means we look at changes and mechanisms that drive these changes in the ocean and timescales that go maybe from the microseconds to decadal timescale. So over, let's say at the most over a lifetime, one would say. Whereas, for instance, Nathan already said is working more with climate, and climate, one could think of it as what are the changes that happen on a very long time scale, and how this also project into the future and so on. So actually, what Rebecca said is quite fitting to this presentation, because what I will try to explain is how we can actually measure the sea level in the Arctic, where most of the year there is at least some part of the Arctic, and always less, of course, but at least some part is always covered by sea ice, which is basically the top part of the ocean that loses heat and get frozen. But first of all, I wanted to go a bit back to the sea level. So what is sea level and how does it change? So we can imagine something like the bottom of the ocean, and then there is a water on top, and at the top, at the interface between the water and the atmosphere, we set the sea surface height. So we will say that our sea level is all the height between the sea surface when it's not moving and when it is moving. Yeah, something like but how, like what makes this surface move? And we can identify mainly two processes, and one is expansion and contraction, which means that water, as any other material, maybe in the everyday life we can think of metals that are expanding or contracting when the temperature is changing and so on. And also water does that, as all other materials. And in particular, the water is changing depending on the heat and the salt content. So it varies with temperature and with what we call salinity. So if we have a very warm water and with very little salt, it would occupy a larger volume than cold water with a lot of salt. And this, in this case, the mass of the ocean doesn't change, but it's simply the ocean is flexible, let's call it, and it expands and contracts. And then the other way in which the sea surface height can vary is if we actually put mass into the ocean, so more water into the ocean. And this, there are several mechanisms by which this can happen. And if you see this funny shape that I made here of the ocean, it's like it's increasing only on this one side, because we can actually have some mass of water that can be moved from one region to another, and then in this specific region where there is accumulation of water, you can actually have a hiring of the surface. And this is what I try to represent here with these two arrows, so all the water going to one place. But we can have, of course, also inflow of water from the atmosphere and from the land. So we can actually have rain on the ocean, and if there is, like, depending on the amount of rain, you can actually increase the amount of water in the ocean. And of course, this is always somehow balanced through the hydrological cycle, but yeah, depends how much rain there is or how much evaporation there is. And the other source is the land source. So when the water in the solid form that is on the land, for instance, on Greenland, there are these very huge chunks of ice that if they come off and they melt into the ocean, they will add water mass to the ocean. And so these are the two main components of the sea surface height variability. So it can vary because it expands and contracts, or because we just put more water into it. And probably what we are comfortable with are more these climate change concepts. So, for instance, for steric changes, one can think of the fact that in time the whole Earth, the atmosphere, and the ocean are warming up, and so this means that the ocean is expanding, and the sea level is rising for this reason. And always on the climatic timescale, the mass change can be primarily seen in the fact that ice that usually is frozen, is in the solid state and stays on land, now with the warm temperature is just melting and flowing down to the ocean. So we are this is just adding mass to the ocean. And these are very complicated mechanisms that actually to be measured required to measure something over the whole globe, or at least in a very large region. So the question that I wanted to pose here is, like, how do we measure all these? And one classical method of measurement in the oceanography is called in situ, which actually comes from Latin and means that you are on the place to measure what's happening. And one very standard way we can imagine is just to have a thermometer, for instance, and you put the thermometer in the water and you see what's the temperature. And that's what we call an in situ measurement. But of course, as I said, the scale of all this measurement is really huge. So how can we get direct measurements of these changes? Here's again my little sketch, and if we look at static changes, we to understand, to see these changes, we need to measure what's the temperature of the water, what's the amount of salt that is in the water, and this can be done with so many platforms, but it requires overall a very huge effort. For instance, it can like the instruments can be lowered from a ship, or even launched from an aircraft. And something particular that we have in the Arctic is this ice coverage. And so there are mechanisms, there are other strategies that have been developed to get data. For instance, some instrument can actually be attached to a buoy that is fixed on the ice, and so it's moving with the ice. And or measurement can be taken when you put an instrument attached to the bottom of the ocean and just floating, and there is a floating device. Or even, especially in the past times, there were measurements done via submarines. But as you see, the extent of the effort that is put to gather this information is really huge. And just not to talk about the fact that also mass changes require additional instruments that have to be placed on the very bottom of the ocean, which sometimes is as deep as 5 kilometers. So this whole is really challenging, and to understand the extent of like how much data we can have through these techniques, we can just have a look, for instance, at this map. Where you can see actually for every yellow point, you will have every yellow point a measurement was made, and this is a particular collection done by Aisbären et al., also a colleague from AVI, and this includes data from a period from 30 years from all ships and submarines and ice data platforms, and this is like a huge effort and a rather sparse coverage over a period of 30 years. So since in the 70s, more and more satellites starts to cover the surface of the Earth, then there's a question: can we actually take advantage also of these measurements that are called remote measurements? So the instrument is actually not in the water, but it's an indirect measurement from the satellites. So, and to explain how this works for CCFSite, I wanted to show a short video that I actually put up myself, and I hope it will work out. It's a very homemade video, but I think it serves the scope. And so what we see is just a satellite is flying over the what we call the ocean topography, so the mountains and the valleys of the ocean. And what we know about the satellite is like how far high in the sky it's flying. This very big red arrow. We do know how high it flies, and okay, wait, we'll do it again. But what the satellite does is to measure its distance to the sea surface. And so we have these two values, and with these two values, we can actually, by difference, determine how high is the surface. But then we come to the problem: if there is ice on top. Oops. Wait. Sorry. If there is ice on top of the ocean, how can we see actually the ocean? But we know that the ice, the sea ice on top of the Arctic Ocean is not one block of ice completely closed and covering the whole Arctic Ocean, but instead is like made up of very many little flows that move around and crack, and every now and then there is what is called lead opening between two pieces of ice, and in between these two pieces of ice there will be the sea surface emerging, and so our satellite can actually measure in between these two pieces of ice. And yeah, and this is basically the very condensed summary of how we can actually measure the sea surface height in a ice-covered ocean. Yeah, and now we go back to looking at like our density of data, and we see, yeah, this is how much we can cover with in situ data and how much can we cover with satellite data. And this is just an example of satellite data that I've been using for my work. And this is just data from 1 month. And you can see, you can fully cover the Arctic Ocean only 1 month. And this is really crazy and incredible, but of course, at the same time, these are very complicated and indirect measurements. They require a lot of corrections and so on. But this is definitely the way to go to have a constant monitoring of our oceans, also in ice-covered regions. Yeah, and if you are surprised by so many points in the ice-covered part, then you can have a look at this at this visualization that is coming from the MIT GCM. So this is a model, actually. It's not observation, it's not the truth, but it gives a pretty good idea of like how to imagine these ice cover on top of the ocean. It's not a full block of ice, but there are many tiny cracks, and the ice moves around. These pieces of ice move around, and there are always new cracks, and so you can always cover new parts of the ocean and really get a nice idea of what there is beneath, at least in terms of sea surface height or sea level, how we want to call it. Yeah, so now that we understand a little bit more how it works, then what do we actually see beneath this cover? First of all, yeah, we talked about topography again before, and I really like this term because it really makes you understand that the ocean is not really flat, but it has mountains and valleys as we have on land. Just they are very much spread out over a large region, and they're much smaller than what we have on land. But this makes you also understand like how precise must these measurements be to get, for instance, 80 centimeters difference over 1,000 kilometers. And so this is this is what the topography of the Arctic Ocean looks like on average. So if we average over several years, we will have that there are some mounts and some valleys that are always there, mostly. And in this case, we can see like there is a very large mount north of Alaska and Canada, and then the surface goes down, and then we have this huge valley that covers almost all the ocean next to Greenland and north of Europe and Siberia. And this is a structure that has been known for a while, but satellite data really manages to give it a precise look at it. Yeah, just to understand a bit more how are these topographic features forming, because of course if we are on land and there is rock, when the rock is there, when the mountain is there, it won't fall down because it's a solid. But how can a mount stay there in water? Like, it's a strange concept, because water is a liquid, is fluid, and we would expect then it falls down again. And so of course, if on the long term there are these features always going on, there must be something that keeps them going. And in this case, it's a wind. So wind in general pushes water here and there. And in this case, we can explain this mount because the winds over this region are circling, like in this clockwise direction. And for some very nice physical processes that are quite difficult to explain now, but when the winds circle like this and push on the ocean, they actually make so that the water piles up in the center of it. And so until the time that we have these winds circling, this mount will stay there. And on the opposite side, instead, the winds on this lower part of the Arctic Ocean are circling in the other direction. And this makes so that the water is pushed outside of the circle. And so we will form this low of sea surface there, like this valley. And this is actually the mechanism that mostly creates the topography on the long term, on the large scale. Yeah, but of course also this feature vary over time because of several processes, and what I've been looking more in detail in my work is how they vary on a seasonal time scale. Like, what's the difference between summer and winter? Just said it plainly. And so here we get into difficult stuff, but I will try to guide you through this map. And these are seasonal differences between winter and summer, which means that I just take the height of the sea surface in winter and see how much higher with respect to the summer it is. And so what you can interpret here is, like, where you see red, the surface is higher, much higher in winter with respect to summer. And when it's blue, it should be lower in winter with respect to summer. And actually this map looks amazing, to me at least, because if you see all these lines, they actually divide the deep ocean from the shallow ocean. So the bottom of the ocean in this part, the central part here, it's probably around 4 or 5 kilometers, whereas close to the coast here, in general, the ocean is between 50 and 300 meters. So there is a very large difference. And we see that the seasonal variability is confined to these areas where the bottom of the ocean is not so deep. So it's really intriguing, and it's the puzzle that I've been trying to solve in the last months. And what I wanted to give a hint here of what could be the cause of it, but I'm still also working on it. So let's see how far we get. First of all, we know that it's a like very large scale, and what can actually cause this on such a large scale, because this is like across the Arctic Ocean is maybe 6,000 kilometers or more. The only thing that can actually do that is the action of winds. And in particular, if we look at, if we imagine this is a section of the bottom of the ocean, and this is water, and this is the surface of the ocean, when we have winds, you see like these are the winds across this section, and yeah, I'm trying to represent this here. What we know is that there are processes and then push the water at the surface to the right of it. So winds blow in this direction will push water to this shallow part. So we wanted to see whether this was the reason why in winter, when the winds are stronger, then all the water was going to the shelf. But when we actually did the calculation, we found that this wind was supposedly pushing too much water on the shelf. Like the amount of water that was pushing on the shelf was so much larger than what we observed. And so basically what we are trying to understand now is whether there are other flows more at depth that compensate this much water pushed on the shelf, and somehow the balance of these two will result in this seasonal pattern that we see here. But this is still a very much open question, and so there you go, a big question mark, and that is actually where my my knowledge of all of these ends. But I hope you got a nice feeling about the ocean and its mountains and valleys and how they can actually change. So I would like to thank you a lot for your attention, and if you have questions on anything that I've said now, I've tried to reply as good as possible. And thank you for giving me the opportunity to give this talk.
Awesome. Thanks a lot for this, a very interesting presentation about the valleys and the mountains in the sea. That's always for me. Yeah, I remember the first time that I heard about it and was like, okay, if you see the ocean, if you look at it, it looks like all at the same height, and then you imagine driving up a mountain with a ship. It feels weird. Great. If you stop sharing your slide, then I can make a short introduction or advertisement for the talk that we will have next week before we go into the questions for you from the chat. So I will just quickly share my screen. And then you hopefully see the slide that we're going to, or for the talk from next week. And the talk will be given by Professor Jelle Beimer. He's deputy section leader of the section Marine Biochemistry at the Alfred-Wegener Institute, and also a professor of marine geoscience at the Jacobs University in Bremen. And he will, something missing, there it is. He will talk about his journey between insanity and hope with respect to the climate crisis. So the talk will be in German. And he will talk about facts about the climate crisis, but also possible ways how to get out there. And so to give also some hope that we can still make it. Yes. So looking forward to hear this presentation next week. But then, let's go back to your talk, Francesca, and I will ask Nathan about the questions in the chat.
Yeah, really nice talk. First of all, Francesca, I really especially liked all your hand-drawn, your title slide and your video.
Yeah.
Cool. So yeah, we'll start with the questions from YouTube. So the first one, isn't it true that gravitation can also influence the sea level? How does it compare with steric and mass changes?
Yeah. So basically, when we talk about mass changes, we also consider the gravity in it, in the sense that, of course, the mass will redistribute following some mechanism, and one that I was explaining is this is this wind, for instance, that pushes water in one place. But of course, also changes in gravity redistribute the mass of water. And for instance, there is so there is also some in some cases a debate when, like, for instance, Greenland is losing mass. So all the mass that is currently on Greenland in form of ice, when it flows into the ocean, it gets redistributed around the world. And so it changes the gravitational field. So sometimes there are confusing results because, of course, even though the mass of the ocean is changing, also the gravitational field is changing. So you have to distinguish these two effects, like how much mass is added and how it redistributes because of gravitational field change. So that's a really good question, actually. It's and this is mostly relevant for long-term changes, because then you do have significant redistributions of mass that change the gravitational field. But for instance, on the seasonal time scale, this is probably little with respect to other processes. Yeah, but good question.
We actually have a second question from Zebra Twist, who posed the first one. And it looks like that's in relation to your final slides, Francesca, which is about that compensation you were talking about. And Zebra Twist was asking, is it possible to measure this deep water compensation with satellites? Like, is it possible with remote sensing?
Yeah, that's actually more tricky. So what you see from the satellite, what I was describing, is mostly the changes that happen at the surface. So let's say it really depends how the structure of the water column is. In some cases, the water column is we can kind of divide it in a surface layer and a bottom layer that are a bit decoupled. So there are different things happening on the surface and below. And this, to describe this, we use a very complicated word, baroclinic. And in some other cases, instead, there is a very homogeneous ocean, barotropic structure is called barotropic instead of baroclinic. And then in this case, what you see from the satellite is happening throughout the water column. But if this ocean is kind of two-layered, we can't really know what's happening down below. Yeah, so probably in shallow part of the ocean where everything is mixed very well because it's quite shallow, we know the whole a bit more of the whole story. Whereas when you have a very deep ocean, the deeper you go, the less you know. Yeah.
Okay.
Yeah. Nice.
Sounds logical, also with the including different words, but I think you explained it very well. At least for me, I could understand what the problems are. And so everyone from the audience, please, if you have any further questions, put them in the chat. Also, as mentioned before, you can also put it in German. We can translate it for Francesca, if that's easier for you. Maybe also Italian, but then we cannot read it, but Francesca has to read it herself.
Or you can say it in German, and I will try to understand.
Right, yes. Making a bilingual episode. So, but then, yeah, I mean, because then I also had a question which was kind of related to what you talked about, the gravitational field, but not really, but it's so. When I had once a course about the Baltic Sea, and there I learned that the land masses of Northern Europe are still bouncing back from the last ice age, and that the sea level is declining in northern parts of Sweden and Finland, so that the land goes up and the sea level goes down, kind of. And is that also, I mean, probably also only long term, but what you can see or has influence on the sea level you're looking at?
Yeah. So yeah, that first of all, that's true. That is probably more affecting the long-term changes. And actually, when you use satellite data, as I was saying, since it's an indirect measurement, one has to correct for so many things, like the fact that, for instance, the measurement is gotten through the atmosphere, and so the atmosphere will also influence the signal. But among all of these things, there is also some corrections for the crustal movement. So actually how the crust below the ocean moves. And this is all a bit entangled, because in some cases, if there are some movements that are even due to the loading of water. So if you have more water that is pressing down, then yeah, you understand. It's really called like loading, like this correction is called loading something. So yeah, definitely this post-glacial rebound has also some effect on the sea surface, but I would say that's not super clear also to me, because I guess on the one side it could be that it's lifting up the surface of the ocean as well, but then you will have a distribution somehow of the water.
Sure. Yeah.
Yeah. So yeah, that contributes as well.
Great, thanks.
Yeah.
I have a question for you from, I do climate modeling, as I said, so a lot of what I'm interested in is in the future in the context of climate change. And you talked about this a little bit as well with ice melting in the Arctic. But I'm just wondering, are there any other effects of climate change on what you were talking about with the sort of topography of the ocean or the seasonality that you've looked into?
Okay. So yeah, the seasonal cycle it's actually a very, very strong signature in the observations, and it's, I would say, rather constant. But of course, then apart from mass going into the ocean, the other component is what I was talking about at the beginning, is the expansion. And actually, especially the parts of the Arctic Ocean that are ice-free. So if you imagine between Greenland and Svalbard and or the Barents Sea, is actually the part that is raising because of temperature increase. So in these parts, you see like a very clear trend in the last 20 years or so, at least. With the sea surface increase, and then in other regions, it's due to other things. So in this mount where I was talking about, actually there is more like the changes are due more to the fact that very, what do you call it, fresh water is getting there, and it's creating some sort of a lens. So in this other region, it's more the salinity that dominates the variability, whereas in the other, in the Eurasian side of the Arctic, it's more the temperature. Yeah, and both. Yeah, but yeah, on the long term, I would guess it's more this glacier or ice sheet contribution and temperature mostly.
Okay, really cool. Yeah, that'll have to be something I keep in mind looking at the model simulations. Nice.
Yeah, good to know.
Francesca, I have what is potentially a silly question, which are probably the best ones here. So I have recently started looking at sea surface height too for my research. And one question I had was, and you explained it really well with that video again, it was just fantastic. Using the satellites to go over the ice, and they're able to look at the sea surface height through the leads, which is pretty neat. However, when I think of sea ice in a way, I imagine that you have a glass of water and you put an ice cube in it, and then the level of the water increases. So do you have to subtract like the mass of the ice to get the sea level height, or do you take into account that there is sea ice there, or is that all just important information that you're able to use?
Yeah, so that's actually a very important question, because it goes back to some preconcept that people have about sea level rise. So if you imagine you have the continent of Greenland, and then you have the ocean, so there will be some ice on top of Greenland, and this is sustained by the continent. So this does not contribute to the sea level, because there is a rock beneath that pushes it up. But while this ice is actually flowing down the slope of Greenland, at some point it will touch the ocean, and it will not be anymore the continent to support it, but it will be the ocean. And in that very moment, this causes an increase in the sea level at the origin, when it actually flows first in the ocean. But the ice that is actually formed in the ocean, so when you have water in the ocean that freezes and becomes ice, it doesn't change the sea level. Basically, if you imagine the ice, you always imagine it half inside the water and half outside of the water, because the volume that is outside of the water is because when the water freezes, it gets this crystalline structure, and it kind of expands. It seems like it expands, but the actual mass of water is the same, you know. So when you have a local like environment with water, and then the top freezes or melts, the sea level doesn't change. So we actually do not need to correct for the presence of sea ice. It's just that's determining also the sea level. Yeah. Then there are also more complicated answers regarding when the ice melts, where does this fresh water go, and so on. So there are regional differences. So if you create ice in a region, like if it freezes in a region and then it melts in another region, since the two regions are quite far apart, there are some effects by which it could actually matter for the regional sea level, but for the global sea level, that's compensated somehow.
Francesca, you explained that so well. Thank you very much. That makes, sense. No, that is okay. That's brilliant. Thank you. I will be able to be more productive with my own research tomorrow because of that. So thanks very much.
Great, always a reason to watch Wissenschaft fürs Wohnzimmer, sitting room science. So to learn a lot. Yes, and also me now trying to imagine the sea ice going, or the transport of water away from one region to another. That's
That's actually quite fascinating. Yeah.
Right.
This block of water, you take it there and then bring it there.
And mailed it somewhere else. Yeah.
Yeah.
Great. All right. And so I think the people are also happy with all your answers. So if anyone has a question that comes up after sleeping one night and dreaming of valleys and mountains in the ocean, then please write your questions to Francesca below the video. We can always, transfer them to Francesca and she can answer them later on. So thanks everyone for watching. And thanks, Francesca, again for the very nice talk.
Yeah, thanks for inviting me.
Yes. And then hopefully see you next week again. And until then, have a good evening.
Bye.
Bye.